Quantum mechanics, it can feel pretty baffling, right? But what if I told you that underneath all that weirdness, there's this incredibly elegant mathematical language? Well, today, we're going to demystify it. We're going to break down the core notation that really makes quantum physics tick. All right, let's jump right in. So here's the game plan. We're going to start with something we all kind of know, vectors, and see how quantum mechanics just takes that idea to a whole new level. Then we'll meet the stars of the show, the Bra and the Ket. We'll look at how they talk to each other, check out the space where they live, and see what happens when matrices get involved. And to wrap it all up, we'll see how one single powerful idea connects all the dots. All right, first up, vectors. Now, when you hear vector, you probably think of a simple arrow, right? Pointing from A to B. But in the quantum world, oh, they are so much more than that. Something way more profound. So over on the left, that's your classic vector. Just an arrow defined by its length and direction. Pretty straightforward. But look at the quantum vector on the right. This thing isn't just pointing somewhere. No, it's this abstract container, almost. It holds everything you could possibly know about a quantum system. Its energy, its momentum, its spin, you name it. It's all bundled up into this one single thing we call its state. Okay, so how do you actually work with these powerful new vectors? Well, a physicist named Paul Dirac came up with this absolutely brilliant notation. And it's all built around two key characters in our story, the Ket and its partner, the Bra. So first, let's meet the Ket. It looks like this. This is basically our go-to way of writing down a quantum state. If you look under the hood, mathematically, it's just a column of numbers. But, and this is a big but, unlike the numbers in a classical vector, these can be complex numbers, with a real part and an imaginary part. And that's super important because that complexity is what gives quantum states a phase, which is absolutely key for describing things like waves and interference. Now, every Ket has a partner in crime, the Bra, which is written like this. The Bra is what we call the dual of the Ket. It's pretty simple, really. If the Ket is a column of numbers, the Bra is just its matching row. You can think of them as two sides of the same coin, two different ways of looking at the same quantum state, and each one has a very specific job. And getting from a Ket to a Bra is a piece of cake. It's a simple three-step recipe. Step 1, you take your column vector, the Ket, and you just flip it on its side to make a row. That's called transposing. Step 2, for every complex number in that row, you do something called a complex conjugate. All that means is you flip the sign of the imaginary part. That's it. It's a totally mechanical process that perfectly links every Ket to its one and only Bra. Okay, so we've got our Bra, we've got our Ket. Now for the fun part. What happens when they actually meet? This is where the magic of Dirac's notation really comes out to play. Think of it like a quantum handshake. It's how we actually pull real, tangible, measurable information out of these super abstract quantum states. When you put a Bra in front of a Ket, they come together to make what's called an inner product. And check this out. See how a Bra and a Ket literally make a Bra-Ket? How cool is that? Anyway, this whole operation takes two vectors, smooshes them together, and spits out a single complex number. It's basically the quantum world's version of the dot product you probably learned about in geometry. And that right there just shows you how brilliant Dirac's design is. The notation just makes sense. When the brackets face each other, closing in, you get an inner product. It collapses everything down into one little number. But what if we flip them? What if the brackets face outward? Well, that is an outer product, a Ket Bra. And instead of collapsing down, this operation explodes outward. You're taking two simple vectors and building a much more complicated object, a matrix. And we'll see in a bit that a matrix is really an operator. The main point here is that you can just look at the notation and it tells you what you're doing. It's awesome. The inner product has another really handy trick up its sleeve. It lets us figure out the length of a quantum vector. We call this its norm. And the way you find it is super easy. You just take the inner product of a vector times with itself. So a Bra of psi times a Ket of psi, and then take the square root. Bam, you've got its length. It's a really neat way to connect these abstract quantum ideas back to something we can all visualize, like the length of an arrow.
So all these Bras and Kets and the stuff they do, they need somewhere to exist, right? Well, that place is a mathematical environment called Hilbert space. I know, it sounds a little intimidating, but don't worry about the name. Just think of it as the official playground for all our quantum stuff. It's the arena where all the rules of the quantum game apply. If you want to get technical, a Hilbert space is just a vector space with some extra bells and whistles. But really, for what we're doing, the only thing you need to remember is this. It's a space that's built with a working inner product. That's its killer feature. It's custom designed for bras and kets to do their handshake thing.
Now, just like our regular 3D world has X, Y, and Z axes, Hilbert space needs a coordinate system. And in quantum mechanics, we call this an orthonormal basis. It's just a special set of vectors that follows 4 basic rules. First, they have to be able to build any other vector in the space. Second, none of them can be leftovers, they're all essential. Third, they're all perpendicular to each other, or orthogonal. And finally, every single one of them has a length of exactly 1. And you know, physicists, they love their elegant shortcuts. They've got a way to pack those last 2 rules, being perpendicular and having a length of 1, into one tiny, perfect equation. It uses this little symbol called the Kronecker delta. And all this equation says is if you take the inner product of 2 basis vectors, you get 1 if they're the exact same vector, and you get 0 if they're different. It's just a super compact and clever way to say a whole lot. Okay, so we've got our states, the kets, hanging out in Hilbert space. But states don't just sit there, right? They change, they evolve over time. So how do we describe that? We need a way to act on our kets, to do things to them. And that's where matrices come into the picture. Because in quantum mechanics, a matrix isn't just a grid of numbers, it's an action.
It's simple. A matrix takes a cat, does something to it, and spits out a new cat. That's why in quantum speak, we usually call a matrix an operator. It operates on the state. This operation could be anything really, a rotation, a measurement, even just letting time pass. It takes your starting state, let's call it psi, and transforms it into some new state, phi. And just like kets have their dual, the bras, operators have their own dual. It's called the adjoint, and you'll often see it written with a little dagger symbol. Now get this. How do you find the adjoint? You transpose the matrix and take the complex conjugate of everything inside. Sound familiar? It should. It's the exact same recipe we use to get a bra from a ket. This is the kind of beautiful symmetry that makes the whole system so powerful.
And because of that symmetry, we get this really neat and powerful rule. Let's say you take an operator, A, and you use it on a ket. Then you take the dual of that whole new thing. Well, it turns out that's the exact same as if you first turned your original ket into a bra, and then used the adjoint operator, A dagger, on it. It just goes to show you that everything you do in the ket world has a perfect mirror image over in the bra world. It all just fits.
All right, this brings us to the grand finale. This is maybe the most powerful idea of all. We're about to tie everything we've learned, kids, bras, basis vectors, outer products, all of it, into one single idea that's like the master key to this whole system. So we already said that our basis vectors can build any other vector in the space. That means we can write any vector, let's call it psi, as just the sum of its little pieces, its projections, along each of those basis vectors. That's what this equation is showing. But I want you to focus on that thing in the parentheses. What is that? It's a sum of a bunch of outer products, all our basis vectors turned into ket bras. This whole thing is acting like an operator on our vector, but when all is said and done, the vector is exactly the same as when it started. So what on earth is this mystery operator that does nothing? And the answer is just so elegant. That mystery operator, it's just the number 1, or what we call the identity operator, the one that leaves everything unchanged. This incredible equation is called the completeness relation, and what it really is a mathematical promise. It's a guarantee that our basis vectors perfectly cover the entire Hilbert space. There are no holes, no missing parts. Our basis is, well, complete. So, there you have it. What we've just walked through is basically the fundamental grammar of quantum mechanics. This whole Bra-Ket thing, it's not just some cute shorthand for physicists. It's a truly powerful and consistent language for describing the weird world of quantum reality. It gives us a way to write down states and a way to write down the actions that change them. And that leaves us with one big, exciting question. Now that we have this amazing toolkit, what fundamental secrets of the universe can we use it to unlock?